welcome back to Tailored Materials and Surfaces. We've got Electroless Deposition this time. It's going to be a little bit of a long topic because we have to sort of take a bit of a run up. So normally we would have electrode deposition where we attach a material, as you know, to a power supply. Let's make it negative. Let's make it negative. This is what we want to make grow. So we want to deposit maybe some copper on there. So we've got the copper 2+ in here. And we want it to discharge at the surface, depositing a layer of copper. We have to complete our circuit, so we need a positive electrode, which would typically in a simple system be made of copper. Whoops, I can't write that, copper. And this would be the plus, so the copper dissolves into the solution, replacing these copper 2+ ions that are discharged and plated onto this electrode, which could be a coin or whatever we want, or a screw or something. So that would normally be electrode deposition. But what if we want to do something else? So we got maybe phone like this. Whoops, how can I do that? Let me put it here. So maybe we've got a phone like this or an iPad or something, which is not metallic to start with. It's a plastic, or it's maybe a piece of glass that we want to coat with a metal. And we would like to do it by electrode deposition, but we can't because it's not conductive at the moment. So if we look at this reaction, for example, we take copper 2+ and we react it with hydride ions, H-. We need to work out how to get those. Then we can make hydrogen gas, sorry, that should be gas, plus copper 0. So we could discharge our copper in solution using hydride ions. The hydride ions will come typically from lithium aluminium hydride or from sodium borohydride. Lithium aluminium hydride reacts with water, so we'll use sodium borohydride as the example here. So we've got NaBH4, and one of those hydrogens behaves like, it's not really, but it behaves like an H-. It can give its electron to copper, making copper 1, and another one can give its electron to copper, making copper 0, forming hydrogen and copper 0. We won't worry about this because this chemistry part, the reduction, can change. So it could also be ascorbic acid, vitamin C, can also donate the electrons. It's a reducing agent. It can donate the electrons to our copper. So what my students should remember is that we used to have a pour-by diagram in our last course where we had the E0, the electrode potential, and the pH to give us a diagram of how oxidizing the conditions need to be to dissolve a metal or to make different species out of it. Remembering that it's a thermodynamic diagram, so we're assuming things take forever, and we would have the metal down at the bottom, metal oxides and other species, typically the metal ion here and a metal hydroxide something anion over this end. So that was a previous version. You remember, or we will consider, that we can change the voltage by attaching an electrode, which is what we do in electrode deposition, and it's what we do if we were trying to protect our zinc boat using an electrical voltage. But we don't have to do that. We could apply chemicals to the water, because if we are doing chemistry, if we're doing an industrial process, we have control. So we can add oxidizing agents to push it up, or we can add reducing agents to push it down. However, there is a problem with the latency, so with activation energies. A simple demonstration of this is the reaction of oxygen with glucose, which we can visualize with a blue dye. It's called the blue bottle experiment. So oxygen will oxidize glucose, but typically you can have glucose in water for a long time and it doesn't oxidize. That's because the oxygen struggles to oxidize the glucose. The activation energy is quite high, and so it's a slow reaction. In high pH, in this case, the glucose will get oxidized by oxygen from the air, but if we leave our solution, the glucose will remove the oxygen from the water, and so the solution will become more reducing. If we shake it, we'll introduce more oxygen, and so we will make it more oxidizing, and that's a dynamic process. The glucose isn't all used up very quickly, so it will recover. If we stop shaking it and stop introducing oxygen to it, the glucose will then slowly reduce all of the oxygen out of the solution, and it will change the redox potential in the solution. So we have a little bit of a problem or an opportunity with the latency of the situation, that it's not a fast process, and that there is some activation energy required, even though this is clearly a reaction that should happen. The oxygen can oxidize glucose, the glucose can reduce oxygen, but it doesn't happen very fast. Obviously, if we had such a solution with oxygen and glucose dissolved in it, then it's not at equilibrium. We can't use a thermodynamic diagram to show it because it's not at equilibrium. It's also very difficult to measure the redox potential of that system. If we put an electrode in and try to measure it, what are we actually measuring? Typically, if we measure the redox potential of a solution, we put in a piece of platinum so that it doesn't affect it too much. And the redox couples in there, so our oxygen O2 going to OH minus. That redox couple and the glucose going to carbon dioxide. Those two redox couples will occur on the surface of our electrode and push its potential up and down. Remembering the important piece of information that we had before, hopefully, that if we have an electrode, let's have two electrodes in there to make it both points at the same time. So this is a copper electrode, there's nothing in the solution, copper 0. So if we got copper electrode, platinum, and we put them in water, tap water, what will happen? Well, the platinum will start getting into equilibrium with the oxygen dissolved in the water. So that's the main redox couple, because there's nothing else really in water, and maybe hydrogen, depending on the pH, but so it will try to reach equilibrium with that, and that will put it to some voltage. The copper will start to dissolve immediately, typically by being oxidized with oxygen, and that will push this electrode. The electrode will get more and more negative, so this one will become negative as the copper dissolves, making it negative. But when it gets negative enough, the copper can't dissolve anymore, and as soon as the concentration of copper in the solution goes up a little bit, it makes it more difficult for the copper to dissolve anyway, so that reaches also an equilibrium. But once that's reached an equilibrium, obviously the platinum now has two things, the oxygen and the copper, that can react at it. But it's a low concentration of copper, so the oxygen is going to dominate here. But now we have a much more important thing that happens in solution if we're trying to make copper. So we've got our copper and our borohydride, our copper and our ascorbic acid, so our reducing agent, and we're trying to reduce it. We're trying to make copper 0, but there is a force against it, which would be, how do we make copper 0? It's in solution to start with. We have to get two copper pluses, squeeze them together, make copper 0. If we make one copper atom, what's it going to do? That's not a metal, that's just a copper atom floating around in water. So we're stuck with a starting problem. If we had a piece of copper, we could make it grow, and that's relatively easy. It takes very little energy to do that. We can see that if we take two copper electrodes and we do the electroplating, which we obviously get to immediately the moment we start to plate our copper, we see that the voltage that we require in order to plate copper is extremely low, because we only need to push one electrode slightly off equilibrium, that it's dissolving, and the other electrode slightly off equilibrium, that it's growing, and they will dissolve and grow. But if we have nothing in the solution, we have a starting problem. We have to generate a new surface. That's difficult. It's difficult to generate a new surface, and so we're stuck. Typically, if we look at that, situation, we would see the concentration. So let's do this with a concentration of something, X. Typically we would have the concentration, which will have a saturation concentration. Let's put it here. So if we had solid in there, it would be at equilibrium. That's the thermodynamic equilibrium, but we're not in thermodynamics here, we're in kinetics. So this would be the thermodynamic equilibrium. That would be where it stops forever. If we start off low and increase our concentration, when we pass the thermodynamic equilibrium, it doesn't mean that particles grow, because we have to make surface. This is only once we've got particles, that is the concentration it would go to. But we can increase our concentration of X far beyond that until it gets so unhappy, the situation, that so our solution in this case gets so unhappy that it starts to make nuclei, that it starts to make new particles. Once it's made new particles, let's have a short piece of nucleation. Once it's made new particles, although we're trying to add more, the concentration will now tend to go down to this point. That's the saturation concentration, but from above. And if we wait long enough, it will actually stop there. So if we wait for infinity time, it will reach the saturation concentration of whatever X is. So this could be sodium carbonate, it could be copper sulfate, it could be salt in water, whatever it is that we want to make. We will first of all nucleate crystals. So this is nucleation. Oh, sorry, nucleation. And this part is growth. From here to here, growth. Why is this important? Well, if we want to use chemistry to grow particles, if we go up to here, or we want to grow, sorry, let's start again. If we want to use chemicals to electrodeposit something, but without an electrode, so we want to electrodeposit glass, we want to electrolessly deposit copper on glass for some reason, then we first of all need to make it start growing on the glass, which is going to be higher than the saturation concentration, but lower than the nucleation concentration, because we don't need to generate a new surface. However, we're coating glass. So it's not as good as coating itself, typically. Can be as good as coating itself, but typically it's more difficult. However, it's not as difficult as making a new interface to water. So if we manage to keep our concentration here and not go past to nucleate it, we can make an unstable solution that will try to coat things that are put in there for all of time. Obviously, an electroless deposition bath is not stable, so we can't keep it for ages, because the moment any particles grow in there, its concentration of, well, we had copper, will go down to the saturation concentration and it won't have any ability to coat anymore. But they are reasonably stable. We can put things in there and grow particles. As a reminder of a similar situation in another course, if we cool water down, typically we will cool it down and we'll get below 0 centigrade and nothing will happen at all, because we can't generate particles, we can't generate ice particles. It costs energy to generate surface until we get down to maybe -9 degrees, maybe -5 degrees, depends on the situation. Then ice starts to form. So we're cooling it down at a constant rate. We're taking energy out of it at a constant rate. So it should be cooling down in a straight line, but it doesn't, because when it starts to freeze, it warms back up to 0 degrees. It's a very similar process. This is supposed to be time, sorry. Then it all freezes, and once it's all frozen, it carries on cooling down at the same rate it was beforehand. A similar effect can be seen with metal particles. So if we want to make silver particles, we can make them with sodium borohydride, for example, as we had with our copper. That will make silver 0 particles. It makes them very fast. The problem with doing that is that the borohydride is an extremely strong reducing agent, and so it will make silver particles over a long time. So we keep getting new small particles. So we get a particle, it starts to grow, then another particle starts to grow as well, and another particle starts to grow, and so we end up with lots of different sized particles in our mixture. If we do it with ascorbate, we have a different problem. The ascorbate isn't a very strong reducing agent. It can reduce silver to silver zero, but it struggles to have enough energy to generate new particles, and so we tend to get very large particles and they get very out of shape. A way to avoid this is to first of all make very small particles with borohydride, and then to grow them with a slower reducing agent. If we look at silver chloride particles in film, which obviously none of you ever use anymore or ever have used, but if we take silver plus, so we take silver nitrate and we add sodium chloride to it, we have an extremely low solubility silver chloride, AgCl, which we want to use to make film. The silver chloride particles are little crystals of silver chloride, and they come in different sizes. However, they're a little bit soluble. So if we leave it for a long time, the smaller silver chloride particles will dissolve and the bigger ones will grow. I think we've had this before, so I don't need to mention it too much. This process is called Osvald Ripening. It generates colloids of all the same size. These are all the same effect, just from different sides. What we want for our electroless deposition is to have a situation where we're gradually applying our metal, but it's not so far out of equilibrium that we can make new metal particles. In this case it's silver chloride, but it works the same with metals as well. Another effect that plays into our hands when we're trying to do metals is that because it conducts, we don't need to do our reduction and our oxidation, at the same place, because the electrons can move through our metallic particle or our metallic surface, whatever we're trying to coat. So in this case, we're trying to coat silver particles that we've made with copper, which we can do by having copper 2+ ions and ascorbate in there, and the ascorbate ions can come along to anywhere on our silver particle. The copper ions can come along to anywhere on our silver particle, and they can react with each other by exchanging electrons. Whereas if they were in solution, they would have to actually collide for the electron to transfer between them. You can't jump through solution very easily, but it can very easily go through the silver particle or a silver surface. So typically what we do with our electroless deposition, you can look it up, it's really easy. Typically what we do is we put one type of metal particles on there first, usually palladium, they tend to stick very well, and then the metal coating that we want is grown with this mechanism. We want to get just past equilibrium, but not so far that we can make new particles, and then we tend to grow and grow and grow on a surface that already exists. Metals are good for this. Metals tend to stick to each other by metal-metal bonding, because the electron that is shared can be shared between different metals, so metals will stick to each other, even if it's not necessarily as good an interaction as it is with itself.